Okay, good morning or good morning
Now,
or good
with a very
evening in
good
Europe.
introduction, sorry. Now, with very good introduction in mind, we will have some of the design ideas and internal workings of the CarpetX by Erik Schnetter. For those of you don't know Erik is a staff scientist at Perimeter Institute for Theoretical Physics, and he also holds adjunct faculty positions at the University of Culpet and the Louisiana State University. He's a maintainer of the Einstein Toolkit, and his research includes high-performance computing with focus on advanced numerical methods, large-scale simulations on relativistic astrophysics, and tools that improve reproducible and collaborative scientific compute. Erik, you can start. Thank you.
Okay, thank you very much for the nice introduction. Thank you. Okay, so I want to continue with Roland's talk. I want to highlight some of the internals of CarpetX and describe some of the design decisions. But before I do that, I want to briefly mention a paper that came out recently called High Impact Scientific Software in Astronomy. And unfortunately, it mislabeled the Einstein Toolkit. It calls it CarpetX here. This is about the Einstein Toolkit. So this paper measures the impact of software in astronomy. And the Einstein Toolkit is actually number 38 in this paper, in all of astronomy. And I think this is really cool. Now, but what this paper does, it defines software as whatever is in a Git repository. And the problem is, of course, the Einstein Toolkit does not have a single Git repository. It's spread over many Git repositories. So this analysis latched on one of the repositories that's currently active, and that's the CarpetX repository, which is why it shows up. But I looked at the data, and it's actually the Einstein Toolkit that they mean here. So what they do is they to measure the impact of software, they don't just look at how many papers have been written with one software, but they take a software, look at all the papers that have been written with the software, and then look at all of the citations to the software. So they want to find out how important is the science that was done with software to the community. And this is where the Einstein Toolkit is important, number 38. I think there are about 26,000 papers that have been written in the past 20 years or so that cite science that has been done with the Einstein Toolkit. That is pretty amazing. And we are not far behind FFTW. That is actually, it's pretty cool. And by the way, Spectre is also there, but it's trailing 2 or 3 places behind CarpetX. So in that figure, it's not currently on the screen. Okay. Anyway, about CarpetX, as Roland mentioned, when we rewrote Carpet to CarpetX, we had 3 goals in mind. It's a complete rewrite because we looked at Carpet and found we had made some design decisions that were not good, and it would be best to start from scratch. And the first goal that is very near and dear to my heart is improved safety. And what we found, unfortunately, is that there's a lot of code written for Carpet that was incorrect. And it's not incorrect in that it crashes or gives wrong results. It's just ever so slightly wrong, and you barely notice. And this wasn't code in the core of the Einstein Toolkit. It was code that people wrote, their own science code. Apparently, it's really difficult to write completely correct code for Carpet. I hate to admit it because, of course, I'm one of the people who designed Carpet. And so we decided to take a step back and put a much larger emphasis on safety. I used to be really gung-ho about performance and so on. If people can't get their code correct, it's their fault, I thought. But yeah, I've climbed down from that ladder. It's really important to make code easy to use and to support students, and you can't leave any trapdoors. Anyway, that was one thing. And the other thing is support GPUs. We made some half-hearted attempt in Carpet, but it was too difficult to put that, to retrofit it in. And I did not like GPUs at the time. I mean, they're so difficult to use. And there's a lot of good science that can be done on a laptop, on a workstation, on a small CPU cluster. But if you want to run with the big dogs, if you want to use the really big machines, it's GPUs. So we needed to put it in. And we also needed to improve the AMR features, in particular, the cell-centered variables and the phase-centered fluxes. When people simulate neutron stars with Carpet, you cannot have a refinement boundary being crossed by a shock. because you lose matter there, you lose energy there. It doesn't work because we don't conserve energy at refinement boundaries. And in CarpetX, we finally fixed that. So these were the 3 design goals. And I'm going to describe that and describe their impact. And if you have questions or comments, please interrupt me. And if you're bored because Roland mentioned that already, please tell me. I can move on and say something else. So about the improved safety, Roland mentioned the declare CCTK arguments that you can now add these other things. Oh no, other things in the X in the end, in particular with the X, and that then looks approximately like that. So here you have some C++ code, you have a wave routine. I assume that you know how to write code for the Einstein Toolkit. So this is how you implement your own routine in C or in C++ with the CCTK arguments. And when you declare your parameters, you add an X at the end, invention of Steve Brand, and repeat the name of the routine. And then the declarations get augmented so that all the constant variables are const declared and all the variables that you shouldn't be accessing are not declared. That helps with correctness, obviously. Now, something else that we did is that instead of you just declaring variables and declaring when to do what with a variable, you now need to give CarpetX much more high-level information. For example, CarpetX has the notion of a state vector. If you solve a partial differential equation, then there's a state vector. This is the thing that is evolved in time. So each variable either is part of the state vector, or it can be calculated from the state vector, or it's constant, something like coordinates or something. And you need to tell CarpetX which is which, and then CarpetX and the Flash can actually make conclusions from that. For example, at the end of a time step, all the variables that are not part of the state vector get invalidated automatically. So if you forget to recalculate the pressure from the internal energy, this would now be caught automatically. But the disadvantage is that you need to carefully think about which variables are evolved and which are not part of the state vector. And that can be quite confusing because most science codes do not work like that. And Roland also already mentioned the reads and the write statements. So for example, when you declare the right-hand side, you say you read the state vector everywhere in all grid points, and you write the right-hand side in the interior. So CarpetX splits the domain, all the grid points in the domain, into 2 different regions. There's the interior and there's the boundary. And the interior is the bit that is evolved in time. And the boundary is the thing that is set via boundary conditions, either physical boundary condition or via mesh refinement prolongation or via ghost zone synchronization if you run in multiple processes. And what you usually do for the state vector, you just write to the interior, and later on you or the system or a schedule routine synchronizes and sets the boundary. And of course, you need to go from everywhere, including the boundary, to the interior because you're having a stencil. So you loop over the interior points, but your stencil, your derivatives, then also look at the boundary points. And here's an analysis routine for completeness, how you calculate the energy density. And it reads the state vector everywhere, and it writes the energy density only in the interior. The energy density depends on the gradient, so it needs to take a derivative, and you need to synchronize the energy afterwards. I think this is everything what I wanted to say. Oh yes, Roland already mentioned. Yeah, I think Roland and I should have talked to each other more closely about what he's going to say. CarpetX keeps track of which region on each variable, on which refinement level, and which patch is actually valid or not. And
Erik,
it can set
actually,
invalid regions to none.
Roland
Hi,
wants
yeah.
to say something, yeah.
Yes, go ahead.
I have a question. Yeah, sorry, you didn't stand much of a chance, unfortunately, of adapting your talk because I really only got mine done 4 hours ago. You mentioned that CarpetX tracks the state vector, and I recall it does that, and it has a notion of dependencies, right?
Yes.
Can you tell us a bit what they are? Because I know they exist, but I don't have enough knowledge to actually say anything about them.
1 or 2 slides further, I'm going to do that. Okay. Very good. And regarding to poisoning, I also mentioned checksums. So if CarpetX thinks a variable should stay constant, then it actually takes a checksum over that variable. And in C++ code, of course, you can always go around things. Even if you get a const pointer, you can use constcast and can still write to things in memory and so on behind CarpetX's bed. So quite brutally, it takes a checksum of all the variables if if CarpetX thinks the variable should be constant. And if you do modify it, then CarpetX will also notice. Of course, only in debug mode. This is quite slow. You can't do it in production, but it helps actually. And here I mentioned the dependencies for improved safety. So here's a declaration of the state vector for a scalar field. That's u, the scalar, and rho, its time derivative. These are the two evolved variables. And via tags, Steve, we should improve that. Get rid of the tags and introduce keywords there. It says that the right-hand side for the state vector is the group called right-hand side, which is defined here. And I name the variables u right-hand side and rho right-hand side. That's a bit boring. And I say that this group should not be checkpointed. And that is the cue for CarpetX, that this variable is not part of the state vector. And therefore, this variable is part of the state vector. We should invert that. We should have some kind of explicit definition of what the state vector is. We kind of stumbled into the necessity for that. There are some improvements to be had. And there are also dependencies. So this declaration here says that the energy variable, this one down here, the energy density epsilon, depends on the state vector. That means whenever the state vector changes, CarpetX will invalidate this variable. Invalidating means it internally, it keeps track which variable is valid and which not. It will invalidate it and fill it with nulls. Of course, this is just the wrong way around, right? Instead of the state vector declaring that the energy depends on it, we should declare in the energy that it depends on the state vector. And we should probably also say how to calculate it so that CarpetX can calculate it automatically. I don't need to ask Steve to do that because he has been wanting to do that since the beginning of the decade or longer. I wanted to make another comment about that. I forgot. It eluded me. Anyway, this is all in the the course of improving the safety of the code. You don't have to use these features, but if you do use these features, it catches many errors and many other things can be caught automatically. For example, when you set up initial conditions, then CarpetX will check that all the variables that are part of the state vector are actually valid. So if you, for example, forget to set a variable, CarpetX would notice that. This sounds all entirely way too low level. Yes, this is the point I wanted to make. All this tracking which variables are valid and not, this sounds horribly low level. In Python, you'd think, if you want to calculate something, you just calculate it in a function and return the variable that holds the result, right? If you want to have a function that calculates the pressure, you just return the pressure from that function. Who needs to keep track of whether the pressure is valid or not, right? Whenever you allocate the pressure, you calculate it right away and all is good. And this, unfortunately, does not work in high-performance computing because allocating memory and deallocating memory is really expensive. It's super expensive. So actually allocating the memory for the right-hand side probably costs more time than actually calculating the right-hand side. This is, I don't know, it's just a weird thing. So you really need to allocate memory ahead of time. And then you're left with these variables that have a very long lifetime that exist through the whole simulation. And then you can't use any of the advanced C++ features to keep track which variables exist or not. They all exist all the time. So you need to introduce these secondary measures to keep track of what is valid and what is not. And this is, I mean, for the sake of performance and GPU programming, we need to do that. It is unfortunate. And if you have a really large science code, as we hear, then you also need to introduce additional metadata to keep things safe. That is just sad, but it's necessary. Now, I already mentioned that the domain and each grid is split into two regions. There is the interior and the boundary. The interior is the bit that is evolved, And the boundary is defined by the boundary condition. So the boundary is not evolved in time. And the boundary could be defined by, say, you say Dirichlet boundary condition or a symmetry boundary condition or some other way. And you probably need to choose for each grid function how you want to define it. What people usually do is they say, oh, now I calculate the pressure, and now I'm thinking how I want to set the boundary for the pressure in this instance. And that's probably not correct. You probably want to take a step back and say, this is the pressure. It's defined from the internal energy and the density. And in my simulation, say, for example, I choose to define the pressure point-wise at every point, including the boundary. And that means you never interpolate the pressure between refinement boundaries. Or you could say, well, I define the pressure in the interior, and in the boundary, I interpolate it from the next cursor graph. It's your choice. But you should probably calculate the pressure the same way everywhere. Otherwise, you can have weird inconsistencies depending on whether, say, the program regrids or restarts from a checkpoint or not. So there are two looping functions. Again, Roland already introduced them. There is loop all device. Oh man, yeah, I'm trying to highlight that with the cursor that my mouse doesn't work. Loop all device loops over all the grid points, and loop int loops over the interior. And then you need to synchronize it in a schedule. And here are some examples, very similar to what Roland showed. I'm going to come back to that example when I speak about GPU programming. So this just means you loop over all the interior points, and the interior code here then runs over all the points. And I was hoping that Roland would introduce the syntax. So U right-hand side is a grid function, and you add this round parenthesis to access a current point.
Hey,
P
Eric.
is the current point, and I is the index. Yes, Stephen?
I just thought I'd mention I did when I did my intro talk yesterday, I actually went through I adapted WaveToyX to building a new Thorn, and I walked through it.
Very good. Thank you. Thank you. Apologies. That time zone difference.
Yeah. Okay.
Yes.
Just letting you know.
Yes. Yes. Very good. Thank you. Thank you. By the way, even Roland and I are in different time zones. Canada is a very, very, very thin and long country. He is 3 hours ahead. So while he was talking, I was still bringing my kids to school. So GPU programming, I don't know whether that was introduced. Was it? Was it not?
I mean, I mentioned that if you write this way, it works on the GPU, and if you have the underscore device thing on there, but not everybody who's listening to this talk may have been at mine.
Okay. So I want to speak a bit about GPU programming and how to improve performance on GPU programs. The point is that writing a code that runs on a GPU is not in any way any magic. You can write your code essentially in a simplified version of the C++ language. There are some restrictions, but in most straightforward code, these restrictions don't apply. You can't have dynamic memory allocation, no malloc, no new. You can't have virtual function calls, and you can't use the standard template library, no standard vector or standard shared pointer or anything like that. Also, in that loop, you can't get out of the loop. There is no break statement. You can't say, oh, I encountered an error, I want to stop the loop. The loop runs beginning to end, because you could think of every loop iteration actually happening instantaneously at the same time. That's the facade that the GPU offers. In reality, of course, it's not like that. You can't you can't have any reductions. That means you can't calculate the maximum or minimum of something. And if there's an error, you can't have a Boolean flag that is set to false before the loop. And then if an error happens, you set it to true to find out whether an error happened. That would also be a reduction. That is also not easily possible. And you can't write to variables that you declare outside the loop. You can read them, but you can't write to them. So the mental model for GPU programming, and that's, by the way, the same mental model as for multi-threaded programming, is that the loop body, the kernel, is converted into a small function. That is actually what the compiler does. And this kernel is called on the GPU, and the loop indices, I, J, K, or whatever, they are passed to that function as an argument. And if you want to access variables from outside the loop, Then they get captured via C++ lumber. Essentially, the compiler declares internally a small struct that contains copies of all the variables that live outside the loop, and then you can access them inside the loop. And that means if you want to access a variable outside the loop, that they need to be copied. You can't have a large array there. I have some example here of how this looks like. So this here is the body of the loop from the real to the right-hand side. That is also called the kernel. This weird syntax with the square brackets and the equal sign is how C++ introduces lambdas. In Python, it's much easier to understand because you just write lambda and then you get a lambda. But in C++, you have this cryptic Perl-like language. You add the cctk device to indicate that this function should run the device. This is the function argument that is mentioned. Point descriptor p that passes in the current point. For efficiency, you can add this attribute always inline, although it's really verbose. And then this loop runs. Now this declares cctk arguments here. This declares all the grid functions like u and row. Internally, there are pointers, and these pointers get copied onto the GPU, so you can access the grid functions here. There are these small structs that wrap the pointers. And one point that is probably not important for completeness, I want to mention it. What the CPU does, the CPU just schedule this code on the GPU, and the CPU down here will not wait until the GPU is done. So if you have multiple loop kernels and the same scheduled functions, they get launched one after the other. They run one after the other, and that is all fine. But if you have first the GPU loop and then a CPU loop, that would break. Because the GPU loop gets scheduled and the CPU loop then might run before the GPU loop has finished because it doesn't wait. Now the capture scheduler will wait in the end, so it's all fine. It's all good in the end. I also, this is a bit theoretical. I hope that Steve's tutorial helped you do that. Now, about the performance GPUs, there's a nice mental model about GPUs, and that is that the GPU cores that do the calculations are infinitely fast. So if you want to optimize your code, the easiest thing to remember is that all calculations are infinitely fast and they take no time at all. The GPU memory is not infinitely fast. So the thing that takes time when you run on the GPU is that each core needs to read data from the GPU memory. It needs to access the grid functions, calculate the stencils, and that is the important bit. So let's look at the code here, this previous code here. I should have used a simpler code. I have a loop here over the different dimensions, x, y, z dimensions. I should have written it out. That would be easier to understand for this example. Let's count how many floating point operations this code does. So this here reads the grid function at one point. This reads another point, multiplies it by 2, and subtracts it. That's 2 floating point operations. Reads another grid functions, 3 floating point operations, and here's a division. That's 4 floating point operations. This happens in a loop that runs 3 times. That's 12 floating point operations. And we need to add all things together. That's 14 floating point operations. I skip adding things to 0 because the compiler probably optimizes this away. So we have 14 floating point operations for one grid point. And in double precision and a modern H200 GPU, 34 teraflop per second, you see this takes about 0.4 picoseconds. It's not the actual time, it's average, right? Because you need to do millions of operations at a time, but on average per operations, 0.4 picoseconds. Let's also count memory accesses. So we're reading, this is a 3-point stencil, so we're accessing the memory 3 times. We do that in a loop in all 3 directions. That's 9 memory accesses. We're reading row here 10, and we're writing the results back. So that's 12 memory accesses.
So
each
Erik,
memory access, yes?
I know that CarpetX has the ability to count the floating point operations for you if you compile it a certain way. Might it be nice if it could also count the memory accesses for you?
It might. It totally might be nice. Yes. Are you putting things on my plate? Is that you taking from me?
Just thought I'd throw that out there.
Yes, no, it's actually straightforward because we already have these grid function wrapper classes. Just remind me, I'll put that in. So we have 12 memory accesses, each reach 8 bytes. The memory bandwidth is 4.8 terabyte per second. So the memory accesses for this loop take 20 picoseconds. And now if you compare these numbers, 0.4 picoseconds, 20 picoseconds, you see there's 2 orders of magnitude difference. So the calculations take about 2% of the time of the memory accesses. And I don't know, astronomy, astrophysics, physics, that's just zero. It doesn't mean anything. If you want, you can repeat all the calculation 10 times, and it still takes only 4 picoseconds compared to the 20 picoseconds. So this is what I mean by GPU cores are infinitely fast. In general, you shouldn't worry about making your calculations faster. You shouldn't worry whether adding or multiplication is faster or saving a division or anything. Most of the time, this is just not where the time is spent. It's memory accesses. So here's a question to you. How could you speed up this loop kernel? Okay, maybe I could coax you into actually answering. If you were all in the same room, I could look at some people. Yeah, I cannot. So one thing would be to actually run this thing in single precision.
Can you
In single
show the code
precision,
again?
each. Pardon?
Can you go back a slide to show the loop again?
That's the
Thank
loop.
you.
So we could run everything in single precision because in single precision, each memory access is only 4 bytes instead of 8 bytes. So the loop would run twice as fast in single precision. If you look at the compute performance, then float and double precision actually is the same on a modern GPU because they don't optimize for single precision anymore. But the memory accesses would be twice as fast. That, of course, is silly. You probably can't run in single precision unless you really closely look at the code. But another way to improve the performance of the code would be to go from a second order code to a fourth order accurate code. In a fourth order accurate code, you need many fewer grid points to get the same accuracy. Now, each calculation in here becomes more expensive. Instead of 3 points, you need to read 5 points. You probably have about twice as many floating point operations. But because you have many fewer grid points, that would improve the performance. And if you go even further, what you could do is instead of finite differencing, where each point has a different stencil that is slowly sliding to the domain, you could go to a finite element method. In a finite element method, you have elements, say elements with 4 cubed grid points. And you load all these data for these 4 cubed grid points onto the GPU cores into registers or cache. And then you calculate all the derivatives for all these 4 cubed grid points from the same data. And then you write this out back. And then you have, in effect, stencils that overlap much more, that reduces the memory accesses quite a bit. And that also improves the performance. So that is the design decision that Spectre made. Of course, there's a big problem with hydrodynamics and so on, which is why we didn't go that route. But if you want to just go for improving GPU performance, that is actually one way to do that. Anyway, and there's another very important word here. It's right in the center of the slide. It is called measure. If you want to speed up the GPU code, don't look at the code. Measure actually what is slow. So you need to run a profile and understand the profiler. I don't think any introduction to that is part of this meeting here, but all the supercomputing centers will offer tutorials every few months or once a year. We have a few hours of explaining how to measure code for GPUs. If you have an NVIDIA GPU, the thing would be called NVIDIA Insight System. It's easy to use. It has a nice user interface and so on. So you really need to do that to see what happens with the performance of the code. And then you also see that these numbers down here, the 0.4 and the 20, they are rough estimates. The reality will be different, quite different indeed. Okay. I want to describe some more internals of the memory, because memory accesses are important, and they're this little bit. The CPU has memory and the GPU has memory, and these are different memories. It's not the same memory. So data needs to be copied between these two memories, and this is slow, but it's the slowest thing on the whole system. AMReX uses a feature called managed memory that GPUs offer, and it automates the copying. You might be familiar with swapping. If you run on a CPU and you run out of memory, then the operating system can copy some of the data in memory onto disk, and then it frees memory for more operations. And this allows you to run, but it's quite slow because copying things from into disk is slow. And what managed memory does, it does something similar, except things are copied between CPU and GPU automatically. I'm not 100% sure, but I think it's a mechanism like page faults where things get copied over as they're needed. The super high advantage is that this is very simple. If you have a loop that runs on a GPU and later on you want to do on a CPU for whatever reason, then it just works. Just run your CPU data loop, the data gets copied over automatically. No one needs to do anything. It works correctly. And you can do that wherever convenient. But for performance, you absolutely must avoid that. So this is me giving you some insight into improving performance on GPU codes. You need to keep the data in one place because the copying is slow, and that obviously is the GPU. What is all your good functions should live on the GPU all the time. And you can use the performance analysis tool to find out when and where things are copied between CPU and GPU. So if you run some analysis...
Erik, I have a question. Yes. So you said that you can't do reductions on the GPU. So does that mean that every time you want to do a reduction, you have to copy data from the GPU to the CPU?
I wanted to qualify that statement. No, you don't. Okay. It's a bit complicated. So if you just want to calculate a maximum or a minimum, there are special ways to do that. It's not simple. And the way we implement CCTK reduce in the Einstein group does these things, and it does not require between CPU and GPU, but you need to jump through some hoops. And if, for example, you just want to check a flag if there's an error, you can use atomic variables, but they need to be on the GPU. That is, you need to allocate memory specifically on the GPU and then create an atomic variable there, and then pass the pointer to that atomic variable to the loop kernel. And then in the loop kernel, you can modify that variable atomically, and that will be, if that happens just a few times, if it's just set an error flag, that will be reasonably efficient. And otherwise, you need to know more about how the GPU actually parallelizes. So in the GPU, you have threads that are organized in warps, that are organized in blocks, that are organized in a grid. It's just a hierarchy. And on each level, you need to do the reduction slightly differently to be efficient, but it does work on a GPU.
Okay, thank you.
I mean, you hear me waffling about, so you see it's complicated. That's why I didn't describe it, but it can be done.
Erik, there is a question in the chat. Kate asks, how does CarpetX handle UMA? Or how is it called? UMI. Unified Memory Architecture. Unified Memory Architecture, right?
Okay.
Yeah.
I do not know what you mean by that.
Kate, can you speak up? Yeah.
Yeah, the DGX Spark Station has the memory is the same for CPU and GPU. So it's all there. You either grab one or the other. They're all the same thing.
Okay. Yeah, very good. So in my mind, when preparing the talk, I thought about NVIDIA GPUs, the why you buy them, the usual. But we're using AMReX as infrastructure, and that works on other GPUs as well. So we definitely run it on AMD GPUs, and Intel has their own thing, and so on and so forth. So these details, memory accesses, are handled by AMReX, and it's quite flexible there. So I assume it would just work. The complications that are managed here with memory, manage memory and slow and so on, would presumably simply not exist on such a system. Does that make sense? I'm obviously don't know all the details here.
Well, I mean, there's no problem when you have unified memory architecture because CPU and GPU memory are the same. So I'm just wondering if you can handle a situation where it has no problem.
Yes, that works. When we first implemented CPU support in Carpet, then managed memory did not yet exist. So we needed to manually copy things forth and back and manually keep track. And that was very cumbersome. So I'm very happy that we don't need to do that thing anymore. But we rely on AMReX here, on the library, and it does everything. So thanks for the explanation. Okay. The last thing I wanted to mention is the improved adaptive mesh refinement. So CarpetX, based on AMReX, supports vertex, edge, face, and cell centering. I have two examples here at the bottom. On the left, you see a cell-centered variable. So all the variables here live in the tiny cells that you see. And here you have edge-centered variables. Edge-centered variable could, for example, be used for the electric field. And there are two kinds of edge centering. So here, this would, for example, be useful for the Y component of the electric field because it's on the Y lines, the grid lines going up and down. And there would be another grid where these little triangles sit here on the X lines. And this would store the X component of the electric field. And that means if you use edge or face-centered variables, and the different components of your vectors of two forms live on slightly different locations in space. And that is sometimes inconvenient, but it has great advantages because it ensures so-called topological properties of the grid. For example, that the curl of a gradient is zero, or the divergence of a curl is zero. Essentially, you say all the magnetic field lines are closed loops, and that's a topological property. They have no beginning, no end. There are no magnetic charges. And these are important properties depending on how you want to model your magnetic fields and your electric fields. And these kind of cell-centered, edge-centered, face-centered variables allow you to do that. Now, technically, what you store is not the Y component of the electric field at this point. What you actually do is you integrate the electric field along this grid line. And you integrate it in the physically correct way, that is taking the space-time metric into account. And that means if you write down how the curl is defined or how the divergence is defined in the end, you get everything correctly. And it is important that you define it that way. So for example, when people say the density is the average density of a cell, you need to average in exactly the right way. Because all the hydropapers do this correctly. That is, you need to take the density, you need to integrate it over the cell using the physical metric, and then you can divide by the coordinate volume of the cell, not the physical volume of the cell. And then you get exact conservation because then all the coordinate-dependent variables can cancel out when you integrate, and you get exact conservation. And in hydrodynamics, for example, if you have a shock going through a fluid interface, I assume you learned that this morning, then mass energy momentum is conserved in that case as well. And apart from pesky problems that Philip Mester can sing a song about, this actually allows having shocks go through refinement boundaries, which is not currently possible, which is not possible in Carpet, the old infrastructure, because in Carpet we didn't have proper cell-centered variables. And finally, regarding improved mesh refinement, it is, due to AMReX, possible to have refined region that can have an arbitrary shape. So if you want to track a shock in a binary neutron star merger, you can do that much more easily than in Carpet, where people never really use that feature. And what AMReX does, First, you mark each cell that you want to be refined or derefined. Next, CarpetX AMReX will block these regions. That is, each 8x8 block will either be refined or not refined. And the number 8, of course, can be changed. And then you have these little blocks that get refined or not. And then these refined blocks get combined into grids for efficiency, because larger grids are more efficient to handle than smaller grids. And this is a nice story, and that works very well on CPUs if you have a low order method. For example, if you have one ghost zone only, first order hydro method, and so on, this works beautifully, has been working for decades. But unfortunately, people want higher order methods with many ghost zones. So that means small blocks, say 32 cubed, are still too inefficient. You want to use larger ones. And if you're running on a GPU, the grids need to be even larger to actually be efficient, to actually be able to run in parallel. And I think you need at least 128 cubed grids or something. And then, of course, the story about tracking exactly where a shock is and refining only close to the shock and not far away from the shock. That story, of course, is then down the drain, because if you have a very large grid structures, then this doesn't work anymore. I do not have a good solution for that. I guess to find out, you need to talk to the people who actually run the simulations. And finally, this is my last slide. I want to advertise some random useful features in CarpetX. Maybe too much detail, but maybe it helps some experts. So I mentioned earlier that the standard template library does technically not work on the GPU. The reason is that the standard template library is compiled ahead of time, and it's compiled only for the CPU, not for the GPU. So if you happen to call an STL function that is inlined, then it'll be compiled for the GPU and it will work just fine. So for example, if you use a standard array, it works just fine. But if you use a complicated function, for example, a sort function or something, and this sort function is pre-compiled, then you cannot call it on the GPU. So CarpetX offers many small classes that do essentially the same as the STL, except it's declared and defined in such a way that it works on the GPU. Interesting is, for example, an R class, sounds like a pirate, which is something like standard array, except it works on the GPU. Oh, here, CPLX, these are complex numbers. Standard complex doesn't work on the GPU all the time. It's really sad. But with this wrapper, you can actually get complex numbers on the GPU if you want, and many other things. We have also helper functions for vectors, matrices, tensors. These are small ones, like you want a symmetric 3x3 matrix for your free metric, for example. You would find this here. There are also some helper functions that should really standardize. For example, for division, if you divide numbers in C or in C++, it truncates to 1, 0. Sometimes you don't want that. Sometimes you have a negative number and you want to round down, towards negative infinity, or you want to call modulo, or you round to the next multiple of 16 and so on. And there are just helper functions for that, because it's more likely to be correct. There are rational numbers. If we count iterations in CarpetX, then we count coarse grid iterations. Of course, the fine grid iterations does half a coarse grid iteration if you take a finite time step, or a quarter, or an eighth, or something. So we represent that using rational numbers, because that is more convenient. There are dual numbers. Dual numbers are up. I don't know. I'm amazed by dual numbers. It's such a cool thing. If you haven't heard of them, read it up. It's like complex numbers, except you don't call the unit I, you call it epsilon, and it squares to 0. Epsilon squared is 0. So dual numbers are for perturbation theory. And if you call, for example, the sine function, and you add such an epsilon thing, then the perturbation is, of course, the cosine function. It's just derivatives. You get derivatives automatically. So if you want a derivative of a function, you can just call it with dual numbers, and then they get the function and its derivative at the same time. You don't have to rewrite the function. You have to use Mathematica for any kind of symbolic manipulation. It's not finite differences with any inaccuracy or something. You just call your function, passing it a dual number. instead of a real number as input. And that's really convenient. For example, if you have an elliptic solver, then you need a Jacobian. It's a bit like, I don't know, like machine learning. You have these, what's it called? Back propagation, dual numbers to forward propagation. And if you want to have an elliptic solver and you want it to run efficiently, then you need for your residual, not just the residual, but also the gradient of the residual. And you can do that with dual numbers. And that is amazing. There's an example in CarpetX that does that. Poisson equation. So it's boring, but you can solve elliptic equation. We have also pointwise root solvers, bracketing root solvers, and multi-dimensional root solvers. These are essentially the routines that we copied just from, how was that famous? Boost, the Boost C++ library. If you call Boost, then it's compiled only for the CPU, so it doesn't run on the GPU. So you take the code from Boost over and you make some really tiny syntactic changes, and then it's compiled for both CPU and GPU. And then many of the nice algorithms then run on the CPU and the GPU as well. So if you want a 3D Newton-Raphson root solver or something, that might just be there in CarpetX. And finally, I mentioned there's an elliptic solver wrapping PETSI library. That's probably not super efficient. I don't think PETSI runs on GPUs. But if you want to set up initial conditions, solve the constraint equations, and you don't want to have to go through the pain of writing your own pseudo-spectral code and then interpolating initial conditions, if you want to solve it right there using PETSI, PETSI is a really good elliptic solver on the grid that you use, then that's there for you to use. Okay, that concludes my presentation.
Thank you very
skip
much.
some bits because Roland already mentioned this. I'm open to questions.
Yeah, thank you very much for your informative talk, Erik. Now we will have questions